Alright, on the bench, the HP 3438A from the large pile of late stuff in the repair queue. This is a 3.5 digit multimeter, so not as impressive as the 6 digit multimeter over here. However, as you can tell, this one you can't see anything because it's LCD. This one should be good LEDs, which you can see from far away and which I can film. So I'm quite interested in this instrument.
Hello, if you follow the channel, you know that we have had several encounters with HP DVMs of all kinds. Some Nixie ones hidden inside frequency meters, some LED ones with many digits, and some LCD ones also with many digits. This 3438A is a donation from Bert at the Hey Bert channel. Thanks very much, Bert. I'll put the link to Bert's channel in the doodly-doo. This instrument has a modest 4 digits, but it is quite small, very easy to operate, and has a very legible large LED display. It is also fully fledged, having an HPIB interface and even rear-facing inputs. So it would be a great tool for lab automation and for me particularly attractive for filming in videos.
And if you turn it on, it has a few, I don't know if you saw that. Yeah, it did turn on. It turns on, turns off. Of course, the scan for the manual from Agilent is unreadable, Keysight is unreadable. So I got one manual, I'll scan it for you all so you can see it. And you can see that the power supply, there's no main switch in it. There is no switch on the main, so the power is always on, and there's just a low voltage switch here, and obviously it's working intermittently. So I think it's a switch issue. These switches, they are very unreliable. We had the same problem with switch on the other 6-digit instrument. Okay, I can hold it, and let's try to, it's in kilo ohms, let's try to put it in volts. Didn't do anything. So I bet you none of those switches are working. And this is a service note for the HP 3438A. Says, occasionally switch contacts become dirty and introduce numerous problems. It is then necessary to clean the contacts, and that's a euphemism for our switches don't work. And then they have apparently 3 kinds of switches. One where the plunger held in place with a metal latch, one where it's with a plastic latch, and one which is the most annoying, that's the one we had in the other instrument where there is a latch here in the middle of the plunger.
If you follow the channel, you know that we had an encounter with similar switches before when we repaired the great HP 3478A. It had 6 digits of utter goodness playing hide and seek on a difficult to read LCD screen. Our instrument had one of these The Village slider switches too. Despite the thick gold plating, individual contact springs, and good contact wipe due to the long throw, it did not make contact anymore. Some kind of invisible insulating material had deposited on the contacts, which I think comes from the outgassing of the plastic enclosure or the plunger. The good news is that it was easily cleaned with isopropanol.
I think it has something to do with the plastic that actually evaporates on the contacts and makes a layer of non-conductive material on it. So some kind of chemical stuff that was totally unplanned. Alright, so that's standard HP. You need your posi drive, screwdriver for the, ooh, I don't think that's here, I think that's here. Okay, the feet, they translate. So this one came with feet. By the way, I forgot to say, this is yet another donation to the channel by my faithful patrons. Okay, and on this side we see nothing because it's all protected by shield. So this is obviously a lower precision instrument, but man, it's just built so carefully. The power supply is partially here, partially down there, and I checked it's all good, so it's really the switch. Interesting how they, for the sake of the form factor, they had to stick the transformer outside. They ran out of space, or that might have been also better for unwanted interference, which is always a problem when you do DVMs. Alright, so now that slide, I remember that, and then you take that out, and off you go. So we're going to take this out, and then this out, and then this out. Boink! Oh yeah, so that's another grommet that's all hardened up. Alright. You have a processor. 1820 1742 Nanoprocessor? Can't remember the number of the Nanoprocessor. Nope, it's not a Nanoprocessor. It's a custom microcontroller. And you believe it, and it has also a whole bunch of hybrids. This is some of the input hybrids that have all the precision resistors and the MOSFET switches. This is just scaling the signal, right? So it's an op amp that scales the signal, but you have to do it very precisely. What is that? Yes, we will have the great pleasure of having a to D made by a series of discrete components. So I think it's a single ramp integrator that then goes into their custom controller, but we should be able to look at this one and see how it does the A to D conversion. I have to figure out how to get in there, and sometimes it screws on the side, but I don't think that's the case here. Nope, holds nothing. And haha, maybe just one more screw. Alright, we have good work access on all of our switches. Oh no, these are the most annoying type of switches to take apart. They have a plastic latch in the middle, which you have to lift to extract the plunger. I had to make a custom pointy tool to lift them up. And when you remove the plungers, you have to be careful not to dislodge the contact tabs and springs. Yeah, just like I did here. Don't do that. You get this in, and then manage to squeeze that inside. Seems like a dangerous thing to do. Oh great, because I got one in and then I got the other one out. Alright, pardon this momentary interruption of the video while I look for my spring.
Moments later.
Okay, let's try to redo the spring thing without undoing the others. Because then when I move the thing down, then of course uncoil the spring on the other side. Yep, yes. Okay, that's the ticket. Do it in the air. Alright. Okay. Let me put a few drops of contact cleaner. I'll put a dab of deoxit on it. There we go. Let's hope that, yeah, it goes in. Okay, and it relatched. Okay, and put the latch back, which is another pain in the butt. the spring goes into the step into the notch, and then we leave the spring, and that should be a contact. Okay, repaired. Okay, point something ohms here. 0.1 ohms. Okay, the next ones are interesting because they're interlocked. Oh, and actually it's those two fight each other. Okay, so I have some interlocking problem. There you go. This one is harder because there are wires in the way. Oh, does it want to come out? Oh, is it because of the latching underneath? Because I had unlatched it there, and I can see it's not held by the plastic latch, but I think it's held by the bar. Yeah, so it's held by the bar that's unlatches one when you latch the other one. How do I get around this? Oh, okay, like this. I just pressed another button and that popped it off. Okay. And look at that. I lost my spring again. See if I've learned something. Yes, I have. I'm getting significantly better at it. Alright. Yeah, so here we have this problem again. So what if I do... There you go. So you have to depress it a little bit. Okay. It's an unlatch. It unlatch partially and then partial press. And it comes out. Okay, we got it. A double. Twice the chances of messing it up. And look at that. I didn't lose any spring. Refuses to get in. So partial press. It gets in. And now we got it. Alright. Out we go. Oh, a triple. Oh, yeah. It's unhappy. Okay, back in. Okay. Nope. Still. They all work, but this one, between the two extremes, there is some difficulty. So let me see how this works. Here, this little teeth, and maybe this one is worn. Yes, it is. This one has a notch in it. I'll have a look in the binocular microscope at it, but I think that's the problem, is that the little pushy thingy has a big notch in it. Alright, so under the binocular microscope, and you'll see it should be pretty obvious. It's more obvious in the binoculars themselves, but there's a notch on the side, and so its lubrication won't help much with that. I really need to smooth this notch out. It should be nice and straight like the last one, and it has a big thing, and it, big dent, and it grabs right in it. Here you can see it right here. So that's my problem. So oops, a little bit. It will need a little bit of micro sanding. Okay, filing wouldn't have worked, but with an X-Acto blade, I was able to take a few shavings. There was a divot in there. See, it's a lot better. So hopefully that will be enough. All right, let's see if the careful shaving and reforming of the wedge is enough to fix it. I might have a divot on the other side too. No, that was it. Okay. No lubrication needed. It was a mechanical surface problem. All right. Well, a few more to do over here. And as I'm trying them, I can see this one has the same problem. This one is tough. It has a divot. All right, so this one will need to be shaved, not only the contact clean, but also have this little surface repair. There we go. Probably a single. It is a single. Let's see if it has the notch problem. Not as pronounced on the other one we just repaired. Let me go look at the microscope. Okay, this one has a related but different problem. It has, I don't know if you can see, it has a notch on top. The divot is right on top. It's missing a bit. Right at the top, right there. So there's a whole bunch of it missing. So once again, lubrication is not going to help that. It's need to be some surface forming.
Soon after.
Okay, so this needed a fair amount of shaving because there was so much material missing. It's smooth, but I reduced the size of the hump, so I hope it will still work. Now it's not hanging anymore. Okay. Oh, and we almost forgot the front back switch, but this one is very accessible. So I can just douse it with contact cleaner. Give it a good twist. There we go. So let's remount it maybe without the screws. We slide the thing back. Okay, temporary. Leave the ground hanging. And hopefully there will be no fault. Alright, the decimal points moves. It went volts, another volt, milliamp went to milliamp, another milliamp, kilo ohms went to kilo ohms. Alright, we will count on success and bolt it back together. Oh! Here's a nanoprocessor. There is one. 1820, 1691. That's a nanoprocessor. So it's part nanoprocessor, part specialized controller. This one has a lot of adjustment. This is all done with little pots all over the place. We need 7 volt power supply adjustment. U725 backgate bias adjustment, clock frequency adjustment 10 kHz, AC 0 adjustment, 20 ohm range 0 adjustment, DC gain adjustment, ohms gain adjustment, AC gain adjustment, 20 volt AC range 20 kHz adjustment, 2 volt AC range 20 kHz adjustment, 20 volt AC range, 100 kHz adjustment, so lots of adjustment. First one is 7 volts. This resistor adjustment, it's 7.0053 on my unreadable meter over there. Okay, so nothing to adjust there. U725 backgate adjustment R603. So that's the backgate for the microprocessor. Let me hook up for that. Backgate voltage adjustment. I am reading 0 volts. I'm not grounded at the same place. Okay, I move my ground to over here. So my ground is different probably from down there to up here. And I am reading -5 on the unreadable meter. 499, so once again it's very close. There's a jumper marked 10 kHz, and you have to make sure It is 10 kilohertz. It's 9.99. We are already in spec. So next is AC0. So I have to short the input, set the multimeter to AC voltage, 20 volt range. AC0, okay, that's this one. So it's slightly off. Okay, we got our 0. Next is the ohm 0, and I think there is a mistake in the instructions. This is set the multimeter to the ACV voltage 200 volt range, and then connect the shorts across the ohms, which is the same as the voltage, and adjust R111 for 0 ohms, but it can't be in the 200 volts AC. It has to be in the 20 ohms. Yeah, correct. That's what it is. It is. 20 ohms. Then I have to be in ohms, right? And does it want me to read 0.00 ohms? Which reads 6, so this is completely off. Alright, finally we found something that was substantially off. Why is it so far off? This is like a mile off. Yeah, I cannot get down to 0. Uh-oh, so we have another fault here. Something is not right. Alright, so we have a big bugaboo in the ohms range. I can make it smaller, but then only so much. I can only go to 3.52. Yes, and then it goes in, okay, it's kilo ohms. And that should be 0 kilo ohms. This is completely wrong. Let's get better. If I put it back in the other direction. Yeah. So I can zero the 2 kilo ohms. And then my 20 ohms at 530. So unfortunately this doesn't bode too well. If I look, this is the 0 adjustment that we are doing. I can do a correct adjustment on all the ranges except this one. Close for 20 ohms and 200 ohms range. So 20 ohms and 200 is the one that gives me trouble. So it makes sense that those get into trouble at the same time. And unfortunately this resistor is, I bet you, in a hybrid. Yes, it is in a hybrid. I saw it. Here is the gray part is our hybrid circuit. Either the resistor or one of the switch transistors in the hybrid has gone bad, which is why we can calibrate all the ranges but not the 20 to 200 ohms. And the proprietary hybrid in question would be U11, that one. That's potentially and probably has a problem on the lower range of the ohms. And of course such a problem might be a user caused problem, right? If you use the ohms range and you put some high voltage in the input, it's the current source is not going to like it. And this was an instrument used in education. I think it's University of Missouri or something like that. Yeah, UMR. So this might be a user caused destruction here. putting a high voltage at the input of the ohm meter in low range mode, I would sure blow it. So let's see if the other functions still work. Okay, for the next test we need the help of my precision power supply, and so right now it's adjusted to, if we could read the freaking LCD, 19.00001, 18.89. We're happy. Okay, 19 volts. Alright, the next step involves setting a precision resistor. So I have my decade box here, and I have it hooked up in 4 measurements. Good. So now we go here, and we are fairly far off. 10 kilo ohms. I can barely get there. So I think my little hybrid has been heated up a little bit and is not as precise as it used to be. My resistor is still 10k. So far, not impressive in the ohms range. Now, interestingly enough, I can calibrate it on the 2 kilo ohm range, 2 kilo ohm range correctly. It's 1.9, 1.899999. Okay, so we are all in agreement. But I think my hybrid is a little wonky. The thing has been heated up too much. Alright, so we have one range that's okay. Then the other one is just definitely short. What about this one? It's completely wrong. Okay, 1 kilo ohms here. We have at least one range that works. And yeah, it agrees, right? So this is 1 kilo ohm. So I think we have mono range ohm meter on this unit. It's only gonna work on the 2 kilo ohm range. Okay, for the next measurement I use my HP 3310, 20 kilohertz. And it's 9.96 volts on here, 9.95 volts on there. So it seems to be in okay calibration. Okay, that's 100 kilohertz. And now what we have to do, 20 volt range, and get it to as high as we can. 10.16. So I need to be at 10.16, which is what my other meter is telling me. Ooh. There we go. We're sort of done with our multimeter, and unfortunately it's not 100% healthy. The ohms range is wrong, except on the 2 kilo ohms, most likely because the hybrid circuit, which does the current source, has been cooked. So wait, I almost forgot. I promised we would take a look at the A to D converter, which is just a beautiful example of dual slope integrator. It consists of an integrator with the capacitor C202. So that's the super main component of this device. It is, let's see if I can find it with the zoom. It is over here. It's the big orange one. I am probing it right now. And what you see over there is the signal on this capacitor going up and going down. Is followed by an amplifier and a comparator. This is to be able to detect the zero crossing. Integrator is here with the integrator capacitor right there. Then there is the amplifier and then there's the comparator right here, and that's the controller chip. So I am monitoring on the capacitor itself. For a fixed period of time, you charge the cap, and then you measure how much it takes to discharge it at a fixed rate. So for example, here, if I go, so you see now I'm charging it up to 19 volts, and now I'm charging it up to 9 volts. It's been scaled up before it goes on the cap, right? The cap charges by about 4 volts here. So let me go back to 0. There you go. So you see that time hasn't changed. It's still 2 graduations, and then but it takes, of course, less of a time to discharge it. And now I go back to my 19 volts. That time hasn't changed, but it charges faster because the voltage is higher, and it takes a long time to discharge it. So the goal is to measure this time, the rundown, as precisely as possible. And in order to do that, they first magnify it. So if you look at it, it looks like a square wave, but it's really not. Let me try to go charge it a little slower. So what they are interested in is to look just at around 0. So they amplify it and then it clips. But you imagine this is the same as the blue curve, but magnified by a gajillion times. And now they can see in detail where it crosses the 0, which is here. There is the exact 0 crossing. So now all you have to do is to measure the rundown, and I picked up that signal starting to count from the beginning of the rundown, and then it stops on the comparator. So those should be aligned pretty exactly. The clever property of this run-up, run-down scheme is that the unknown voltage can be inferred by the ratio of little t over big T times the reference voltage. The result is totally independent of the value of capacitor C, resistance R, and even the long-term stability of the clock used to count big T and little t. Compared to the multi-slope 2 instrument that we saw that can extract 2 more digits, this is very simple. This is also very slow. It takes several hundred milliseconds to measure one signal, so it's super slow. But it's a just beautiful implementation of a dual slope A to D converter. Alright, she's all done, and with reliable readings, at least on the volt scale. So let me know if you have one of the hybrids laying around. You can actually see the beautiful digits on front of the display. Maybe only 4 of them, but super easily readable.